Now, in the previous example, you may be wondering how we had a calculator that showed a decimal number or a base 10 number, a number that we human beings typically read like 125. Now, knowing that this is hardware, that decimal number has to be represented as ones and noughts because you can only have bits, positive and negative charges, and those bits can either be on or off, or 0 and 1. A bit cannot be in both states at the same time. So our decimal number 125 has to be represented by a base 2 number. But how exactly has this come about? How do we actually know that this is the correct base 2 representation of our base 10 number? Well, to find this out, we need to understand how to work with binary. So first of all, what we want to do is we want to take a look at the system. We need to know how many bits we're working with first of all. Are we working with an 8-bit, 16-bit, 32-bit or 64-bit system? We need to know how many bits we're working with. Well, as you know, we're working with an 8-bit calculator, a calculator that can process 8 ones and zeros at one time. So we're working with an 8-bit system. So in order for us to calculate this decimal number in binary, what we need to do is first of all draw 8 boxes. And what our binary data represents is actually decimal numbers, and that number is either turned on or turned off. And by simple addition, we can find out the base 2 number. So if you're a little bit confused, don't be, because here's how you do it. Step 1, draw your boxes for how many bits you're working with. Step 2 is start with the least significant bit on the right-hand side. This is the smallest number, and as we go through, we keep doubling the number till we go to the most significant bit, which is the very last bit on the left-hand side. So we start with the least significant bit and we start with the number 1. So we start with the number 1 and then you keep doubling for each box. So we go 1, 2, 4, 8, 16, 32, 64 and then finally 128. Now there's something really magical about these numbers. These numbers can produce any number within the given range. Now to find out the range, what we need to do is we need to, let's say, turn all of the bits off. Now don't forget your bits can either be off or on. Now if they're off, we ignore the decimal number above. That number is switched off. So if you switch all of those decimal numbers off and you try to add all of them together, they're all switched off, so you end up with 0. But then to find out the range, the maximum number we can produce on an 8-bit system, we want to add all those numbers together. So what do? We turn all of those numbers on. So we set all of our bits to 1. And when you add 128, 64, 32, 16, 8, 4, 2 and 1 together, you will end up with 255. There is our range on an 8-bit system. We can generate any number between 0 and 255 and represent that number as a base 2 number on an 8-bit system. So now let's take a look at our calculator example where we had the number 125. How do we find out the base 2 representation of the number 125? Well, it's actually very simple. You have to go through a process of subtraction starting with the most significant bit. We start on the left, just like reading a book, you start on the left and then you go to the right. So we're starting on the left-hand side. And what we're trying to do is get down to 0. We're trying to subtract away from 125 till we get to 0. Now, can you take away 128 from 125? Now don't forget our bits can be on or off, 0 and 1 or yes and no. So can it be subtracted? The answer is no, so we turn that number off. It either fits or it doesn't. So we simply turn it off. The next up we have 64. Now what we want to do is we want to say, can we take 64 away from 125? The answer is yes. so we can turn that bit on. That bit represents the number 64. So when you take away 64 from 125, you are in fact left with 61 as the remainder. And we're just going to keep going in this fashion till we have no remainder. So can we take away 32 from 61? The answer is yes, that leaves a remainder of 29. So we turn that bit on. The next bit is 16. Can 16 be taken away from 29? Yes, it can. It leaves a remainder of 13. So turn that bit on. Then we have the next bit, which is 8. Can you take 8 away from 13? Yes, you can. That leaves a remainder of 5. Then we have 4. Can you take 4 away from 5? Yes, you can. It leaves a remainder of 1. Can you take away 2 from 1? No, you can't. So we turn that bit off. It's either on or off, yes or no. And finally, the least significant bit, the number 1, can you take 1 away from 1? Yes, you can, and it leaves you with the value of 0. So there is our binary representation. When you add 64, 32, 16, 8, 4, and 1 all together, you will get the number 125. So there is our base 2 binary number that represents the decimal number, the base 10 number of 125 in our hardware as positive and negative charges. It's that simple. Now also you could have, let's say, another number and be quite lucky. Let's say you have 128. So somebody types that into the calculator. Well, again, clear it all out. The first bit is the most significant one, and that is 128. 128, take away 128, leaves you a remainder of nothing, 0. So all of these other numbers you can't take away from 0, so you can immediately just switch all of those bits off. You're already at 0. Once you reach 0, the rest of the bits just switch off. So take a number, for example, of 45. Now I'm going to leave you to do this exercise. I type in 45 into the calculator. Pause the video and see if you can come up with the binary representation, and make sure you don't start on the right-hand side. You are guaranteed to get it wrong if you start on the right-hand side. Always start from the left and go down, just like you read a book. So hopefully you get the correct answer of the base 2 number that represents the decimal number 45, and that is 00101101. And that is 32, 8, 4, and 1. Those bits are switched on. You add them together, you will get the number 45. It's easy. So what I want you to take away from this lecture is, first of all, you need to work out what bit system you're working with. 8-bit, 16, 24, 32, 64-bit system. And you need to draw those boxes out. So I've drawn 8 boxes out because I'm working with an 8-bit system. You start with the least significant bit, which is on the right-hand side, and it represents the smallest decimal number, which is the number 1. And then as you keep doubling, you will eventually end up at the most significant bit, which is on the left-hand side. And this represents the largest decimal number. And all your bits, either 0 or 1, are turning that decimal number on or off. It's that simple. Those bits represent those decimal numbers. It's that simple. And if we switch the bit off, a negative charge or 0, that decimal number becomes of none effect. We ignore that bit, if you will. And if that bit's turned into a 1, a positive charge in the hardware, that bit is turned on and it represents the decimal number according to the place where that bit is. And of course, all you need to do is you need to just take any decimal number within the allowed range, and all you have to do is switch all the bits off and switch all the bits on, and you'll find the range for that bit system, and then pick a number between those two numbers, or even the max number or the min number. It's entirely up to you. And then of course you can represent that number by starting on the left hand side with the most significant bit and just keep going down and keep subtracting away until you get to 0. Once you hit 0, if there are any remainder bits, then just switch them off, and there it is. So hopefully now you can see that counting binary is actually the most simplest thing you could actually do.